Okay, now, in the last video we saw how the fatty acid was going to be entering the skeletal muscle cell and then entering the matrix of the mitochondria to perform the oxidative reactions on the fatty acid to generate energy. Now what we have in the mitochondria matrix is the fatty acid structure, and we're going to be performing the reactions, series of 4 reactions, in order to release the energy from these from the fatty acids. Now what I'm drawing here is the portion of the fatty acid that is going to be worked on first. So here's our fatty acyl-CoA structure in the matrix of the mitochondria. And our ultimate objective of these reactions of beta oxidation are to release an acetyl-CoA group. Here is an acetyl-CoA group. So if we remove these 2 carbons with this carbonyl and this thiol linkage with the CoA group, that will be acetyl-CoA. So the process of beta oxidation is going to be releasing 2 carbon units at a time with the acyl linkage of coenzyme A, so that we have the product to put into the TCA cycle. Now the reason that this is called beta oxidation is because recall the nomenclature of fatty acids. The carbonyl carbon is carbon number 1 of the fatty acid. So this is number 1, 2, 3, etc. However, the other nomenclature is that this carbon is the alpha carbon, this is the beta carbon, recall this is the omega carbon. So we are going to be performing these oxidative reactions primarily on this particular carbon, the beta carbon, hence the name beta oxidation. Now the first step in this reaction is that we are going to need to modify the beta carbon to prepare it for the next steps of reaction. And what we are going to modify is the bond between the alpha and beta carbon. We are going to be introducing a double bond between the alpha and beta carbon. So this double bond is going to be introduced by a dehydrogenase enzyme. The enzyme is called acyl-CoA, referring to the original fatty acyl-CoA structure, dehydrogenase. Now also recall that when we're introducing a double bond between carbons, these are single electron movements. This is not forming a 2-electron hydride ion. So in order to perform this reaction, we are going to need our redox pair, and in this case, the molecule is FAD, to form FADH2. So we're transferring 1 electron each from these carbons, putting it on FAD to generate FADH2. The remaining electrons between the 2 will collapse between them and form our double bond. So this is our first oxidative step. Notice we've generated some energy stored in the form of FADH2. Now the next reaction is performed by an enzyme called hydratase. Now hydratase simply is a hydration reaction, and we are going to be adding water across this double bond. The water will be added such that the beta carbon is receiving the hydroxyl portion. So now we've prepared the beta carbon for a next step of an oxidative reaction. And the next structure is going to be an oxidized form, which is going to generate more energy. And that energy is going to be stored in the form of NADH. Because in this reaction we are going to be oxidizing this carbon-hydrogen bond on the beta carbon. We're transferring these two electrons as a hydride ion to the NAD to form NADH. And in doing so, we're transforming this alcohol into a ketone structure. This, of course, is a dehydrogenase enzyme. And the specific name is beta hydroxy acyl-CoA. Again, reflecting the acyl-CoA that we are working with a fatty acyl group, similar to the first reaction, and beta hydroxy because we have a hydroxyl group on the beta carbon. Now, once we have this structure with our ketone structure on the beta carbon, we have a simple reaction which is simply going to be adding CoAsh to this carbonyl. So the sulfur of coenzyme A is going to perform a nucleophilic attack on this beta carbon, and in doing so, it's going to release this 2-carbon unit. So what we will generate is a fatty acid that is 2 carbons shorter than the original. Whoops. Let me draw this correctly. This enzyme is called a thiolase. Thiolase simply because we are using a sulfur group as a nucleophile. And in doing so, notice that we are removing these 2 carbons with this coenzyme A attached, and that is forming acetyl-CoA. This acetyl-CoA structure now can enter the TCA cycle by condensing with oxaloacetate. We will fully oxidize the acetyl-CoA into CO2, and recall from this TCA reactions we will obtain 1 FADH2 and 3 NADH molecules per acetyl-CoA that goes into the reaction. Now, just from one round of fatty acid oxidation, notice the amount of energy that we've generated. Just releasing 2 carbons of a fatty acid structure, we've generated 2 FADH2s and a total of 4 NADHs. Now, the reason that fats are so energy rich is because recall that our most common fatty acids are 16 carbons long or 18 carbons long. We also have some fatty acids from plant structures that are even longer than this, 20, 22, and 24 carbons long. But just picture from just a simple 16 carbon molecule, this will give us 8 acetyl-CoA molecules. So if one acetyl-CoA molecule generates a total of 2 FADH2s and a total of 4 NADHs, including that which derive from the TCA cycle and that from the beta oxidation reactions, we have the equivalent of 6 high-energy molecules generated per acetyl-CoA. If there's 8 acetyl-CoAs in one molecule of fatty acid, now we can generate 8 times 6, 48 reducing equivalents to put into the electron transport chain. So one molecule of fat generates an enormous amount of ATP. Now, the remaining product, we just talked about acetyl-CoA, the fate of acetyl-CoA going into the TCA cycle, but what about the remaining product? So let's say that we started out here with a C16. By the time we get down here, we've removed 2 carbons as acetyl-CoA, and we are left with a C14 molecule. So what do we do with this? We take this C14 molecule and we place it back into the oxidation cycle by the acyl-CoA dehydrogenase to begin oxidizing the new beta carbon of the C14. So we go through this particular round of beta oxidation a total of 7 times for a C16 fatty acid to generate our 8 acetyl-CoAs.